Lesson 6, Optimization. Optimization is one of the most common applications in calculus. We often hear terms like least time, greatest profit, shortest distance, maximum volume, minimum waste. In order to optimize problems of this sort, we first need to find the quantity that needs to be minimized or maximized. Students often find this to be a challenging lesson to master due to the difficulty presented with finding the quantity to optimize, the constraints, and then writing equations for each part of the problem. Just be sure to read the problem carefully, then identify the quantity to be optimized and the constraint. If a quantity is stated to be a fixed value, this will be your constraint, which must be true regardless of your solution. The best thing to do with these problems is do examples, and as you do different types of examples, you kind of feel more comfortable doing these types of problems. So example number 1, find two positive numbers such that the sum of the first and twice the second is 64, and whose product is a maximum. Okay, so we've got two positive numbers. So we're going to say let x equal the first positive number and y equal the second positive number. And then our function, it says such that the sum of the first and twice the second, the sum, there's positive, of the first and twice the second is 64. Okay, this is not going to be the equation that we're taking the derivative of because they're asking for whose product is a maximum. So when you see the product is a maximum, you know that you're going to be maximizing the product equation. So whose product, which would be x times y, is a maximum. So what I did was I just called this, what did I call it? I called it f of x. Even though there's a y there, because what we're going to do is we're going to use this equation, we're going to solve for y, and then we're going to substitute that back in right here for y so that I will have all f of x. So they gave us a constraint. This was considered the constraint. This has to be true. Okay, so we've got this constraint right here, and then this is what we're going to maximize. So we have to know what we're maximizing. We have to know, maximizing or minimizing. For another problem, it might be minimizing. And we also typically have another relationship between the variables. So if we solve for y, first thing we would do is subtract x from both sides and then divide by 2. So our y equals 32 minus 1/2 x. So now we've got f of x equals x times, and instead of y, we're going to put 32 minus 1/2 x. And then I'm going to go ahead and distribute that x. Now again, this is the equation that we're going to maximize. When we say we're going to maximize it, we're going to take the derivative, we're going to find the critical point, and then we're going to find the maximum. Okay, so you know how we found critical points and then we looked to see which one was a max and which one was a min. Using our sign chart, going from plus to minus would be a max, minus to plus would be a min. We're basically doing the same thing here, but we want to make sure we're going to maximize. So we're going to find the x value that maximizes it. So we're going to take the derivative. 32 minus, when I bring the 2 down, that becomes a 1, x, set it equal to 0. I'm going to add x to both sides. X equals 32. So now, I want to make sure that this is my maximum. So I'm going to look at f prime of x, something less than 32. How about 31? If I put that back into my derivative, 32 minus 31 is 1. That's a positive number. If I chose 33, 32 minus 33 is negative 1. That's a negative number. So I know that this is my maximum. If my x is 32, if x equals 32 maximizes it, then I'm going to put that 32 back into my constraint to see what my y is. So I put 32 plus 2y equals 64. I'm going to subtract 32. Divide by 2. And I see that my y is 16. So these are the numbers that under your constraint of the sum of the first and twice the second is 64, this is going to give you your maximum product. Okay, example number 2. A rancher plans to fence a rectangular pasture adjacent to a river. Okay, so we are going to draw a rectangular pasture and I'm going to say it's adjacent to a river. So I'm going to draw a river like that. Since it's adjacent to a river, they do not need fencing along the river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. So square meters, when you see the word square meters there, you know that's area. So this is a constraint. Your area must be 180,000 square meters. What dimensions would require the least amount of fencing? Okay, when you see least amount of fencing, you're thinking, okay, well, my fencing is going to go here, here, and here. And I want to minimize that least amount of fencing. So you want to minimize. So we're going to minimize the amount of fencing. So what are we going to do? Well, we're going to call one of these X and one of these Y. And if this is Y and that one's X, then that's also X. So my perimeter equation that I'm going to minimize is going to be 2x plus y. So this is my minimize equation. How would I use my 180,000 meters squared? How would I find the area of this? I hope that in your mind you're saying x times y. So your constraint is that x times y has to be 180,000. Okay, that's your constraint. So now, when we go to minimize something, we've got p is an unknown, x is an unknown, and y is an unknown. When you're doing optimization equations, you can't have three unknowns. So, you know, if I made this p f of x, I'll put or f of x, then I would want to get rid of my y because I want my function all in terms of x. And right now it's 2x plus y. It's not all in terms of x. So if I were going to take this constraint and solve for y, 180,000 my pen's not liking me tonight, divided by, oops, sorry, I said divided by 2, divided by x, and then put that into this equation. You can change it to f of x if you want. You don't need to, but 2x plus 180,000 divided by x. And that was just putting that in for y. So now, I'm just going to get rid of some of this from the last problem. Now you're going to, I hope you remember, you're going to take the derivative and you're going to find your critical points. And you're going to hope that one of your critical points, or maybe it might be the only critical point you have, but you're going to be hoping that that one is a minimum this time, because we are trying to minimize the perimeter, because we're going to minimize the fencing. And that perimeter was what gave us that fencing. All right. So now, f prime of x is equal to 2, and this would be minus 180,000 over x squared. I hope everyone saw how I got that derivative. And we're going to set that equal to 0. Since that's negative, I'm going to bring it over to this side. Multiply by x squared on both sides. Divide by 2. And square root. We aren't going to put plus or minus because we're talking about a value, you know, like we're talking about a distance here, so it could never be negative. 300. So your x is 300. Now, we're going to make sure it's a minimum. We're going to be looking at f prime of x here. I'm going to pick, let's say 200. And if I put that into my equation, I'm just going to go to my calculator and I'm going to say 2 minus 180,000 divided by 200 squared. And I'm going to get a negative value. And then if I put 400 into that same equation, I get a positive value. So I have just made sure that that was a minimum. So now you need to go back to your constraint and see what happens whenever you put your answer for x in. So if I put in 180,000 divided by 300. That gives me a y value of 600. So for those constraints, the minimum fencing is going to be when your x is 300, and this would be meters. X is 300 meters, and your y is 600 meters. That is going to minimize the amount of fencing that you need. Okay, example number 3. An open box is being constructed from a piece of sheet metal, 18 inches by 30 inches, by cutting out squares of equal size from the corners and bending up the sides. What size squares should be cut to make a box of maximum volume? So when you see maximum volume, you're going to take the volume equation for this box, because what's going to happen is you start out with a rectangular sheet of metal, and it says it is 18 by 30. So 18 inches by 30 inches. They're going to have you cut little squares out of every corner. They're going to be x by x squares. And when you get done, you're going to fold them, and you'll fold them like along here, along here, along here, and along here. Okay, these are going to be gone. Okay, take out on each one of these corners. And when you fold it up, you end up with a box like that. So by folding up this piece, that makes the height of my box X. Since I've cut out an X here and an X here, this distance that's left right here is going to be 18 minus 2x. And I've cut out this distance x and this distance x, so this distance here is going to be 30 minus 2x. So my volume of this box, length times width times height, is going to be x times 18 minus 2x times 30 minus 2x. And we want to maximize this. So notice that it's already in terms of v and x. So it just has two variables, which is what you want. Okay? So you don't have to worry about any of your constraints. Your constraints were already in there by starting out with an 18 by 30 inch piece of sheet metal. Okay? So your constraints are already taken care of just by saying that that's the size of your sheet metal. So we want to know what size squares should be cut to maximize this volume. So we still have to take the derivative. So what I'm going to do first is I'm going to just multiply. So the first thing I multiply is my 18 times 30, and that's going to give me 540. 18 times negative 2x is negative 36x. Negative 2x times 30 is negative 60x. And negative 2x times negative 2x is positive 4x squared. And of course you have your like terms here. So we've got x times 540 minus 96x plus 4x squared. And then you need to distribute your x, and I'm going to put them in order also, meaning I'm going to do x squared, x, and then, or this will be x cubed. So I've got 4x cubed minus 96x squared plus 540x. And this is what we're going to take the derivative of. If you wanted to, you could say v prime of x. You don't have to. This is going to be 12x squared minus 192x plus 540. And I want to set that equal to 0. And I notice that I can factor a 12 out of every term. Now I want to see, can I factor that? I tried to factor that and I could not. So quadratic formula. So you could also use completing the square if you wanted to, where you, leave a space and end up putting it in vertex form. But let's go ahead and use the quadratic formula. My a is 1, my b is negative 16, and my c is 45. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So we have 256 minus 180 underneath the root. And remember that you can go 16 divided by 2 plus or minus. And then this would be the square root of 76 divided by 2. So you can put that 2 underneath both of them. 76 is divisible by 4. So this becomes 8 plus or minus. And so if it's divisible by 4, it's 4 times 19. Then I can go, the square root of 4 times the square root of 19 is 2 root 19 over 2, and the 2's are going to cancel. So this is going to be 8 plus or minus the square root of 19. If I put that in my calculator, 8 plus the square root of 19 gives me 12.359. So 8 plus the square root of 19, 12.359. And 8 minus the square root of 19 gives me 3.641. So 8 minus the square root of 19 is 3.641. So now, you always want to look at your smallest side. So let's go back up here. My smallest side was 18, right? 18 and 30 here. My small side was 18. Since I am cutting out x from both sides, I cannot have an x larger than half of my smallest side. So for my domain on this function, my domain had to be between 0 and 9, because I couldn't have made it 9, because then I would have cut 9 off one side, 9 off the other side. I wouldn't even have had a side. So therefore, when I look at my 8 plus the square root of 19, I'm going to have to throw that one out because it's greater than 9. So my 8 minus the square root of 19, 3.641, that is going to be the one that I keep. And if you wanted to, you could put your 3.641 just to make sure that you've got a maximum, and you could look at your v prime of x. And so if you put in like a 2, you know, you could put a 2 into this derivative here. 48 minus blah, blah, you know, whatever. I can't remember what I got, but I did make sure that this was a maximum. I did get a positive, and I got a negative when I put a 4 in. So you just want to put a value that's smaller and a value that's larger, but you want to keep it in your domain. You couldn't have put a 10 in because your domain only went to 9, okay? So, although 10 would have worked for this one. But you did want to make sure that you've got a maximum. So that is going to maximize. So what does that mean? That means that those are the squares that you need to cut out if you want to maximize your volume. If you want that box to hold the most amount, then you need to cut 3.641 by 3.641 little squares out of every corner, fold it up, and that will give you the maximum volume. And then what is that maximum volume? Well, since our volume equation was x times 18 minus 2x times 30 minus 2x, I can put 3.641 in and calculate that volume. And I got 886.552 cubic inches. So, and so that was also my volume of 8 minus the square root of 19. So that's more exact. So you wouldn't have wanted to put your rounded thing in and then round it again. You want to put that exact 8 minus the square root of 19 in. So then we say that the volume of approximately 886.552 cubic inches will be maximized by cutting squares from the corners of the sheet metal that are x equals 8 minus the square root of 19 inches, because v prime of x equals 0 at x equals, I'm going to say approximately 3.641 inches. And signs change from positive to negative at that x value. Okay, so if you're supposed to justify something, you know that you're justifying why you know that that is going to give you that maximum, okay? And so you're explaining that. So now we've gone to just listing some strategies for solving an optimization problem. Number 1, you have to read the problem carefully, underline key information, make sure you know what you're maximizing or minimizing, make sure you know how to write your constraint equation, draw a picture. Always is very helpful. Label the constants and variables for unknowns. So you're going to have things that don't change, almost like, you know, the length of a ladder. Like if a ladder is sliding down a wall, the ladder's length is not going to change, but the ladder's distance away from the wall will change. Number 3, write a primary equation, an equation that gives a formula for the quantity to be optimized. So that's your max or min equation. Identify the constraint, that limiting factor, and write a secondary equation and an equation that provides information needed to complete the primary equation. This equation will determine the domain constraints. Number 5, solve the secondary equation for the variable to be optimized. Plug it into the primary equation to create an equation in terms of a single variable. We didn't want x and y on some of those, so we went ahead and solved our constraint equation for y and substituted so that we were taking the derivative with respect to x only. Number 6, simplify the primary equation and determine a feasible domain. Differentiate and find critical values within your domain. Determine the absolute extrema and justify. Answer the question in a complete sentence using the appropriate units. There are situations where if you have endpoints for your domain, that sometimes your endpoint actually is your max or your min. So you do have to be careful and you do have to consider your domain on some of these problems. Okay. Example number 4. In the last few examples, we were guaranteed that the functions had absolute extrema by the extreme value theorem. Let's explore a few situations for which the domain is neither closed nor bounded. Example number 4, what are the dimensions of an aluminum can that can hold 40 cubic inches of soda? And guys, look at your units because that cubic inches tells me that that's volume. Okay, so my volume, 40 cubic inches. And that uses the least amount of aluminum. So if I'm thinking that my can is, like the top of it and the sides of it, all along here, everything, that is all my aluminum, that's going to be my surface area. So for this problem, the least amount of aluminum tells me that I'm going to minimize surface area. And so I should be thinking, what's the surface area of a cylinder? So surface area of a cylinder, I've got 2 pi r squareds, right? Because I've got this part up here and this part down here, so that's the top and the bottom, plus, and then do you remember if I take the perimeter of the top times the height, so 2 pi r times the height. So that is my surface area equation. That's the one I want to minimize because they're wanting me to find the least amount of aluminum, but it still has to hold 40 cubic inches. Okay, so I do need to know what is my volume of a cylinder. And please remember that volume is area of the base times the height. So for this one, it's going to be pi r squared times the height because our base is a circle. So we know that our constraint is that pi r squared times the height has to be 40. That is your constraint. And so that is what you're going to be using. You're going to have to put that in because right now you've got your surface area is an unknown. Also r is an unknown and h is an unknown. So we have too many unknowns here. So they want us to tell them the dimensions of the can. So we're going to have to tell them R and H, but we have to decide how are we going to solve, are we going to solve this equation down here for R or are we going to solve it for H? So we have to decide that. So now, think about both of those scenarios. Okay, if you were going to solve this for R, you would divide 40 by pi and h, and then you'd have to take the square root, or because you've got r squared, so you wouldn't need the square root for this r squared, but you would for this other one. So you have to really think about that. I think it's probably going to be a better idea to solve for h. So if we were going to solve for h, we would have 40 divided by pi r squared. Okay, let's try that one. Let's do that. We're going to take that constraint and we're going to say, okay, we have surface area equals 2 pi r squared plus 2 pi r, and then n for h is going to go 40 divided by pi r squared. You can see that your pi's will cancel here and that one of your r's will cancel, but you'll still have one down there. So your surface area equation becomes 2 pi r squared plus 80 r to the negative 1. It's 80 over r because 2 times 40 is 80. And then there's only thing left in the denominator is r, but I'm going to bring it up as r to the negative 1 so we can take the derivative. Because we're trying to minimize the surface area, so we need the derivative of the surface area. I'm going to bring the 2 down times that 2 pi is 4 pi r, and this is going to be minus 80 r to the negative 2. So that's over r squared. And this is what we want to set equal to 0. And so since this negative 80 over r squared is, well, since it's negative, I'm going to add it to both sides. Then I'm going to multiply by r squared on both sides, because I want to get rid of that denominator. So 80 equals 4 pi r cubed. Divide by 4 pi. R cubed, and then look, divide by 4, divide by 4. R cubed is 20 over pi. And then we take the cube root of both sides. So my r is going to be the cube root of 20 over pi. I'm going to put that in my calculator to see what that approximate value is. So my r is approximately 1.853 inches. And if you want to make sure that that is giving you a minimum, you can do your little sign chart with your surface area prime. You've got your 1.853, and I did that, and I put a value less than it in, and I got a negative. I put a value greater than it into the derivative, and I got a positive. So I verified that that was a min. So if our radius is 1.853, I can go back to that h equals equation. H equals 40 over pi, and then I can put my, and remember, always put your exact in so that when you do that in your calculator, you're not rounding it 2 times, because then you get further away from your answer. So I went ahead and put my true answer for r in there, the cube root of 20 over pi. And so and then I put that in my calculator, and I got h to be approximately 3.707 inches. And so now I would say that, and if you were, needing to justify, you could justify it. The can measures radius approximately 1.853 inches, and height approximately 3.707 inches, with volume 40 cubic inches of soda. Since the surface area prime of 1.853 is 0, and the surface area of R changes signs from negative to positive there, we know that those dimensions are going to give us that minimum surface area. Okay? Oops.